Earthquake Fair Testing, we will be investigating earthquakes, which are sudden geological processes that affect Earth's surface. Why earthquakes happen. The Earth's outer layer has sections called tectonic plates. The plates move continuously, but opposing plate movement causes pressure on materials in the crust. Tectonic plates can move in various ways. They can slide under one another or push up against each other. There are different fault types. Convergent, where plates move into one another. Divergent, where plates are pushed apart. And transform, where the plates move sideways against each other. The rocks in the crust are elastic and gradually become distorted by this pressure. Compare this to an elastic band being stretched. The band has a maximum stretchability. When this is reached, the band breaks and snaps back, releasing stored energy. Earthquakes occur when rocks slip past each other along the fault plane. When this pressure is released, it causes shock waves that vibrate the Earth's surface. Earthquakes tend to occur in the upper levels of the Earth's crust. Earthquakes and seismic waves. When seismic energy is released, it radiates outward through the surrounding crust as several types of waves. P waves or primary waves are compressional waves. They are the first and fastest kind of seismic wave and travel quickly through rock. They push and pull the rocks they move through and also move through fluid. They travel at the speed of sound as a series of contractions and expansions, pushing and pulling particles in the direction of their travel. S waves or secondary waves. The second type of wave you feel in an earthquake. They are slower and move at about half the speed of P waves and can only move through solid rock. They are shear waves that push material at right angles to their path of travel. Surface waves ripple across the Earth's surface, and these waves are responsible for the most damage. Rayleigh waves roll along the ground like ocean waves and cause most of the shaking. Did you know that waves travel so fast that they sometimes reach the surface before the rupture itself? Did you know that sometimes the actual earthquake is so slow that it cannot be detected by human senses and does not generate shaking? Focus and epicenter. The focus or hypocenter is the point of initial rupture where the radiation of seismic waves travel from. The epicenter is the projection of the hypocenter on the Earth's surface. Science core concepts. The important concepts concerning earthquakes are faults. A fault is a fracture in the Earth's crust where the rock mass on either side has been displaced. Earthquakes occur on fault lines. Inside the Earth is divided into layers. The surface is divided into plates. These tectonic plates move constantly. Seismic waves. Seismic waves are waves that travel through or over the Earth. They are usually generated by movements of the Earth's tectonic plates.
We are basing our experiment on the Science Australian Curriculum Strand ACSSU 096 for Grade 6. Sudden geological changes or extreme weather conditions can affect Earth's surface, with the elaboration investigating major geological events such as earthquakes, volcanic eruptions, and tsunamis in Australia, the Asian region, and throughout the world. This is the scientific question we base the experiment on. Is the damage to buildings more severe closest to the epicenter of an earthquake? As a group, we hypothesize that the damage is more severe closest to the epicenter of an earthquake. Fair test information. The constant in this experiment is the number of blocks, height of blocks, and shape of the block tower, the amount of force, the blocks and the stack, and the base or earthquake testing system. The change or the variable is the distance from the point of impact. And what we are measuring is the number of blocks that have fallen.
Details on the model. After discussion, much research, and considering various materials and methods, such as polystyrene and boards on wheels, we decided on the model construction. Two boards were attached together using 4 springs bolted to each board. A vital variable was the force. In order to obtain a constant force, we decided to hang a heavy object on a pendulum suspended at a constant height. A bolt was chosen as the object that would be lifted. The bolt would be released or dropped, so that the force of gravity acting against air resistance would be the same for each experiment. A tape measure was attached to the model to ensure a constant height and distance for the bolt to be lifted at 34 centimeters. The size of the model was debated, and it was agreed for the base to be 65 centimeters and the building platform 50 centimeters. The scale of the model in relation to the force, size, and weight of blocks, the friction and surface of blocks, and flexibility of springs proved to be challenging. The point of impact was initially on the top board and represented the focus. Later we changed it to the bottom board being the focus and the top board representing the epicenter. We drew measurements on the board as markers to place the blocks at 10 centimeters. 4 3-centimeter wooden blocks stacked on top of each other proved to be a usable size and weight in relation to the scale and stability of the model and the magnitude of the force for our experiment. We placed the model on a thin rubber desk mat to reduce excessive vibrations in relation to the size of the model. And that concludes our model.
In this experiment, we are measuring the damage as the amount of blocks that fall after the point of impact is hit by the bolt. See how the bottom block in this recording rolled over onto its side. In this trial, we would count 4 blocks of damage. If the bottom block had stayed in its place and not changed sides, we would have counted it as 3 blocks of damage. The experiment. To make the testing as fair as possible, when setting up the trial, we needed to ensure the blocks were placed directly on top of each other. We needed the model to protrude over the edge of the table so that we had an unobstructed impact zone. This overhang was measured at the beginning of each trial to ensure fair testing. We then lifted the bolt, measuring the drop distance using the tape measure, ensuring the flat side of the bolt was facing the impact point. The bolt was then released and we recorded the damage.
So what you do, you have to make sure the mat's on the edge,
Oh, so I'm doing
and then you get the ruler and you make sure it's at 10.
10, yeah.
And then you just double check this side.
Yep. Make sure it's not
Yeah, so it's even and not
even, yep.
skew.
And how far are we doing it up?
You make sure the flat part of the bolt is down, and you lift it to 34.
34.
And then you make sure you get the tape measure out the way.
Yeah.
And then drop it.
Cool. Trial at 20 centimeters. Trial at 30 centimeters. Trial at 40 centimeters. This table shows our results from all our trials. We completed 10 trials at each interval. As you can see, most of the trials at the 0 and 10 centimeter intervals caused more significant damage. We found that the further the blocks were from the epicenter, the more inconsistent our results became. When we calculated the averages, the results became clearer that the closer the blocks were to the epicenter, the more damage was caused. The results at 30 centimeter interval were inconclusive due to a structural fault which we will discuss in our limitations. Therefore, our hypothesis was confirmed. We did our best to complete a fair test, but there were limitations due to human error. We dropped the bolt from the same height each time, and although we ensured the flat end of the bolt was always facing the point of impact, we could not guarantee the exact same angle of the bolt each time it dropped, which affected how the bolt hit the point of impact. Fair testing was not completely achieved due to a structural fault we discovered at the end of our trials from the results chart. Due to lack of support at the center of the platform, there was a slight dip that may have affected our results. We suspect that springs placed evenly throughout the structure would have contributed to more consistent results. We also believe that a model with a longer platform may have been more suitable to prove our hypothesis.
Our real-life link relating to this experiment is the Haiti earthquake of 2010. The Haiti earthquake hit at 4:53 p.m. on January 12, 2010, some 25 kilometres southwest of the Haitian capital of Port-au-Prince. The initial shock registered a magnitude of 7.0 and was followed by two aftershocks of a 5.9 magnitude. It was initially believed that the earthquake was caused by the movement of the Caribbean tectonic plate. However, with no surface deformation was observed, this was ruled out as a cause. The earthquake was generated by contractional deformation along the Léogâne Fault, a small hidden thrust fault discovered underneath the city of Léogâne. 3,500,000 people were affected by the quake. Over 220,000 people were estimated to have died, and more than 300,000 people were injured. The damage of this earthquake was so significant that at least 1.5 million people were left homeless. While it is now 2016, 6 years later, more than 62,000 people still remain without housing due to this earthquake.